The plan for this lesson is to discuss data transformation methods. We will cover normalization, including min-max, z-score, and decimal scaling. After that, we will move to discretization and hierarchy generation. Very often in the data analysis process, we need to map the entire dataset to a new form or scale in order to apply an algorithm or run a tool that requires the data to be in a particular form. There are several methods to perform data transformation, and it all depends on the data type, data range. Are we working with discrete values or continuous values? Some of the methods that we will discuss here are smoothing, normalization, and discretization. In min-max normalization, the goal is to transform a value that already has a minimum and maximum to a new minimum and maximum range. Let's work through a concrete example. Suppose a grade range is 15 to 50 and we want to normalize v equal 30 to the new range of 5 and 17. Let's break down the formula. And I'm going to start from the end because it's easier. A new minimum is the lower end, and it's going to guarantee that we're going to get the lower end regardless of what's going to happen in this part. A new max minus a new min is this interval's width, which means if I add the new minimum to the interval width and this part was equal to 1, then I'm going to get the upper limit, which is 17. Now let's take a look at this ratio. What does it mean? So v minus minimum over maximum minus minimum. So this is a ratio that represents where the original value lies inside its own interval. So is it in like the 50%, 25%, 90%? And I'm going to multiply it by the width so I know exactly where this value should be. So if you plug the numbers in the formula, you're getting 30 minus 15 over 50 minus 15, then you multiply it by the width, which is 12, and add 5, and this is how we got 10.13. In z-score normalization, we subtract the population's mean from the value and divide over the population's standard deviation. And the z-score means the distance between the value and the population mean in terms of standard deviation units. So we can say something that the value is within 1 or 2 standard deviations. Here's a concrete example. mu equals to 54,000, sigma 16,000, and v equals to 73,600. We plug in the numbers and the normalized value is 1.225, which means it's within 1.225 standard deviations from the mean. In decimal scaling, the goal is to transform very large values to fractions. And the way it works, we divide each value by 10 to the power j, where j is the smallest integer, such that the maximum of the absolute value is less than 1. In this example, the maximum is 10,710,000. So j is 8, and then dividing each value by 10 to 8 is going to give us those fractions. Discretization means that we're going to divide a continuous range of values into intervals because working with intervals is much easier. We can do summaries, identify the upper end, lower end, the middle, and it's a form of data reduction. And there are multiple methods to perform discretization. We will go over binning, histogram analysis, clustering, decision trees, and correlation analysis. The simplest form of discretization is binning, and in the equal width case, the data range is divided into intervals of equal size. And this is very simple and easy to implement, but it's not going to work well when there are outliers or the data is skewed. So some bins might end up empty or with very few values. On the other hand, equal depth or frequency binning is going to divide the range based on the frequencies. So each bin should satisfy some frequency threshold, which is very great for data scaling, but in the same time, it's going to be tricky to deal with categorical values because they don't have natural order, or maybe some categories are more frequent than the others. And here's an example to show smoothing by bin means. The data are sorted, then partitioned into equal frequency bins, and then we use the mean as a smoothing value for each bin. And in this example, we use bin boundaries. So we're going to assign each value to its closer boundary. So 8 is closer to 4, 9 is closer to 4, 24 is closer to 25, and so on. The visualization example shows how a data set was partitioned using the equal width binning. And as you can see, the method ended up splitting the data in the most dense part because the implementation is straightforward. It's just look at the width and it doesn't look at frequencies or distributions. On the other hand, the equal depth method has slightly improved on the previous method, but still there is no separation between different classes. So the second bin has data points that belong to two classes, and similarly the third bin. So for this type of data sets, clustering works the best because it's going to create partitions where the data members are similar to each other. Classification and correlation analysis can be used as discretization methods. In classification, which is a supervised learning method, we assign labels to the data, which is similar to discretization in some sense. Similarly, a chi-square analysis as a discretization method groups continuous values into interval based on their statistical similarity or correlation, which will also result in manageable and interpretable dataset. Concept hierarchy generation for nominal data is the process of organizing categorical data into multiple levels of abstraction, which will be helpful in analysis and summaries. Also, it allows presenting the data in different level of granularity depending on the task. In this example, we can see how the address can be presented in different levels of granularity. So the upper levels of the hierarchy will be more abstract and the lower levels will be more detailed. In summary, we covered normalization techniques including min-max, z-score, and decimal scaling, discretization, and the concept of hierarchy generation for nominal data.